Okay, we're good to go. So thank you all for coming. Good morning. Today we'll be talking a little bit about what's actually happening when we are dealing with flows and processes at the microscale. But first I'd like to apologize looking a little bit casual today. I had some very trustworthy intelligence that there may be paint and dye stuffs being spread around today around campus. So I was advised to get a t-shirt that could get colored and full of paint. So I'm not sure what's going to happen today, but I'm very excited to learn more about the traditions around Holi. And for all of you, tomorrow we'll all have a day off, and I'd like to wish you a happy Holi.
Same to you.
Thank you. So yesterday was a tough day. There were lots of equations, lots of mechanisms, but I hope that at the end of the day, doing the simulations and playing with that, actually consolidated all the information with the trust. It was all valid and built on first principles. And you could then apply that in the different software packages in order to either design but also understand the mechanisms behind electrophoretic separations. By the end of the day, it is a physical process. It is driven by equations we understand really well. And because there's so many equations involved, we need these simulation packages to calculate what's happening. But once we've got this calculation happening, it makes the understanding develop a lot faster when you can do it on your computer than when you would be in a laboratory with an instrument making up 20 different buffers and optimize your separation. So if you're not a big fan of equations, and we just had a little conversation here offline, if I need equations, I'm good at that in the morning till about 11. If I need them, I can write them down, work them through. The later it gets in the day, the worse I get with equations. So you don't necessarily need to be an engineer and absolutely comfortable around all of the equations. All you need to do is understand that what you're doing is based on equations. You can get back to the basics if you need to, because they can help you predict what's going to happen, and with that, design your experiments. Today will probably be our last day of equations. So today we'll be talking about different types of actions we can do with the flow, because flow behaves very differently when we work on the microscale than it does in everyday living. And I didn't have my animations switched off yet. So let's stay here. So we need to understand when we're talking about a microchannel what's small. And if we've got a microchannel that's got a certain size determined by the characteristic length, the characteristic length is 4 times the surface area, so the width times the height, divided by the perimeter. The engineers really like normalizing conditions. Just see if I can quickly switch the animations off, because that's otherwise. Where was that? No. I'm not sure where I can switch it off. I'll look at it later in the break, because a couple of my slides have the automated timings in there. But yeah, normalizing parameters is very useful, because that means that you can move from a rectangular channel to a square one, and your physical models don't have to change. If we think about dimensions, it is important to realize that our volumes shrink by the size to the power 3. So if we go from a cubic decimeter, which is a liter, to a cubic centimeter, that's a milliliter. So we've got a factor 1,000 here, 3 orders of magnitude, by just dropping 1 order of magnitude from a cube that is a decimeter by decimeter, so 10 centimeters by 10 centimeters, to a cube that's a centimeter by centimeter by centimeter. we go from the total volume there from being a liter to being a milliliter. If we then go another order of magnitude down in our dimensions of our cube, we end up with a cubic millimeter. Again, we take 3 orders of magnitude in our volume there. So we have a volume of a microliter, which is kind of as small as we can easily, comfortably see. If you look at the in the biology, microbiology labs, there are the autopipettes. There's wide pipette tips. You can go down to well, maybe half a microliter. But a microliter is still something you can comfortably see. Smaller volumes become really hard to see, but the scaling works the same. So if you go to a tenth of a cubic millimeter, we end up with nanoliter volumes. If we go even smaller, we end up with picoliters, all the way down to the point where we go to 1 cubic micrometer, which is kind of the order where we're working in microfluidics. Our channels are typically 20, 50 micrometers wide and high. So this is the order where we're working, which means that we're working in the order of femtoliter to picoliter volumes. This is where we know how things scale. We're another 3 steps down. So that gives you a little bit of an idea how small the scale is that we're actually doing our chemical experiments with when we're working with microfluidics. This was the other graph that we already looked at on Monday that shows that graphically slightly differently, where we've got the scale going from meters, millimeters to micrometers and nanometers. We are with microfluidics typically in this area up to about 500 microns. So this is where we're working, which is at that femtoliter to nanoliter volume. It is also the same size as cells, bacteria. So we start ending up in a size domain where actually we could work very well with cells and manipulate single cells because our structures are at a similar size to what the size of a single cell is. So, but yeah, please keep in mind that our volumes scale down and we're typically talking about high femtoliters to low nanoliters when we're working with microfluidics. When we are working at this small scale, it means that diffusion starts to matter and diffusion becomes faster. So here we've got a human hair. It's about 100 to 200 micron in diameter, depending on ethnicity. I've got very thin hair, so my hair is probably around 75. Your hair may be a lot thicker, close to 150 to 200 micron. It's also about the size of a grain of sand. So if you really look closely, you can see it, but it is hard to start distinguishing the detail. We know that the distance that a molecule diffuses depends on the square root of the diffusion constant multiplied by the time. And the diffusion constant in turn is a function of the size of your molecule. So larger molecules will diffuse a lot slower than smaller molecules. So if we look at an antibody, which is large or small relative to acetate. Antibody is a large molecule. It's a protein, and its diffusion constant is about 40 square micron per second. Whereas a small molecule, for example acetate, but you can take any small molecule drug, pharmaceutical, the diffusion constant is about 1400 square micron per second. So we have, if we let our molecules diffuse freely, we have a significant difference in the speed at which our molecules randomly diffuse. If we start off with a mixture of an antibody and a small molecule, and we come back after a second, our antibody will be kind of close by to where we originally deposited it, because its radius will be about 40 square micron, where it has been able to diffuse to. Whereas our acetate is all over the shop, orders of magnitude further ahead. So the acetate will diffuse in the same amount of time a lot further than our large molecules like our antibodies. So in 5 seconds, the antibody can move over a distance of 20 micron, whereas the antibody will cross 100 micron, which directly provides a great opportunity for some level of separation. Because if you want to remove your acetate from your antibody, you could actually take resample close to the location where you started, and there will be a lot of your acetate will be further away than your antibody. At the same time, if for example we want to do an immunoassay and we have a microchannel that is 100 micron wide and our antibodies are sitting at the surface. For an antibody, it takes 125 seconds to reach the surface. But for a small molecule, it only takes 3.6 seconds. So again, we can manipulate our surface interaction of our molecules if they're from the center of the channel. Because if we stay shorter than a minute in the channel, the antibody is very unlikely to even see the walls when it started at the middle. Because it takes 125 seconds by diffusion to get to the outside. So that's molecular property, predictable, and we can work with that, trying to separate small and large molecules. But we can also take it to calculate what the time is that we need for an immunoassay. And this 125 seconds to cross 100 micron is why, if you've done ELISAs in molecular biology, why you need to wait so long in a microtiter plate. Because the dimensions in a microtiter plate are not even in micrometers, they're in millimeters. And you need to have times for your antibodies and antigens to find each other and bind. And that takes time, so that's why the long incubation times are required to allow diffusion to take its time, take away. If we look at flow, at the microscale we are typically looking at turbulent flow. Here you can see some smoke example, so this is some particles released into the air. And you can see that there's all kinds of eddies and swirly whirlies because the particles, based on differences in velocity in the air, will go everywhere. Same when we look here at a garden hose. If the water comes out of a garden hose, it doesn't necessarily go into a straight line. You can see the very similar swirls as we know from the smoke. We can also see them in water. If we look at a river that's flowing, and you put a little stick in, you can see that the stick doesn't necessarily move in a straight line, but there's all kinds of curves in there, and they are caused by convection. When we work at the microfluidic scale, however, our flow is laminar. Which means that all the flow lines, and therefore particles or solutes, move along smooth paths and lines in an area where the viscous forces are the key players and the inertial forces are negligible. The inertial forces were the ones that caused all the swirly whirlies. We can get rid of them. Again, hard to imagine, but if you think about honey, honey's got a very high viscosity, and therefore it is really hard to mix something into honey. So honey is the nicest example. So water in a microchannel at a small scale, and again we'll be going through some equations after this to show the underpinning physics. But water in a microchannel behaves very similarly to honey in a jar. And if you've got some food dye, we've got a day where we're doing a lot of things with dye anyway. If you try to mix some food dye in a jar of honey and you try to stir the spoon, you'll actually see that the dye that you're trying to mix in exactly follows the path where you're dragging your spoon through, and it is not going around like your milk would be normally when you're stirring your tea. So any of the processes that we're talking about in water, think that this water in a microchannel behaves like honey, because that is something that we know about at an everyday scale. So the Reynolds number is one of these dimensionless numbers that engineers really like to talk about. And if we have turbulent flow or laminar flow, is defined by this Reynolds number. And under a Reynolds number of about 2000, the flow is considered laminar. So you can calculate your Reynolds number in a system based on this velocity, the viscosity, and the length of the system that we're working in. So the Reynolds number is the ratio of the inertial forces over the viscous forces. And that is then the product of the density, which as a chemist you're comfortable with, the linear velocity, so the speed with which you're moving, the characteristic length, and again that is that weird thing that we started off to be able to work with cylindrical, square and rectangular channels. So that says something about your geometry and the size of your channels, divided by the dynamic viscosity. So the Reynolds number you can calculate if you understand your fluidic properties and you know that the speed that you're moving at. If we go through an example, and here turbulent flow, we've got our swirly whirlies. That is the convective mixing. Think about the smoke, but also think about if you're pouring some milk in your tea, you can see the milk swirling around. So that is turbulent flow. We are now thinking about laminar flow. And if we do the calculations, we've got the equation here. If we've got water, the viscosity of water is about 9 to the minus 4 Pascal second. The density is 1 gram or 1,000 kilos per cubic meter. So if we've got a tube that is 10 by 10 by 10 centimeter, and we're stirring at a speed of 10 centimeter per second, which is something that you'd be doing by cooking. The Reynolds number in this instance is 11,000. It is our everyday life, and indeed, if we work in our everyday life, we are in the turbulent flow because 11,000 is larger than the 2,000, which is kind of the cutoff point for being turbulent flow if you're larger, laminar flow if you're lower. However, if we go to a channel that is 100 micron by 100 micron, still working with water with exactly the same properties, where we've got a density of 1,000 kilos per cubic meter and a viscosity of 9 times 10 to the minus 4 Pascal seconds, only by downscaling from 10 by 10 centimeter to 100 by 100 micron, our Reynolds number all of a sudden drops. We're working at the same velocity. Our Reynolds number drops to 11, which is significantly smaller than 2000. So our flow behavior changes into the laminar flow regime. I already mentioned honey, and honey has got a greater density than water. The density of honey is 1420 kilograms per cubic meter. It also has got a larger viscosity, about 14 Pascal seconds. And that's what we know, honey is a lot more viscous than water. In a 10 by 10 centimeter tub, again stirring at exactly the same velocity, our Reynolds number is 1. So our Reynolds number is significantly below 2000, and therefore we're in the laminar flow regime. So that's where my hypothesis or my idea came from, that we can consider water in a microchannel in a fluidic context like honey in a tub or a jar that we are using at home. So processes, it's a lot harder to stir things through, it's a lot harder to get proper mixing. But if you put some dye in, you can actually trace your tracks because your fluid is not going to be moving anywhere. One of the ways that we've used this slow diffusion is that you can have liquids sitting side by side. So this here has been a hydrodynamic injection system that we've developed a couple of years ago, where it was a capillary electrophoresis system, so just ignore the channels coming to the sides for the separation. At the moment we're looking here at the center part where we introduce the flow. So we've got a sample flow here coming from the bottom, And then we've got 2 bits of buffer flow to shield the sample flow. Because we're in the laminar flow regime, these 2 flows will actually stay alongside each other. And we've got a picture coming up shortly. At the point that we want to inject the sample, we can stop the buffer shield flows, which means that our whole flow then is for a very small amount of time only our sample, and we can introduce a small amount of that sample into our separation channels. Then we clean everything up, so we stop our sample, we put our buffer all the way through, and then a separation can be run. So you can use these shielding flows of one reagent to prevent the diffusion of your sample into your separation system, just by the fact that the flow is laminar and all the transport is governed by diffusion, which particularly if you talk larger molecules is a really slow process. Picture says 1,000 words. So this is how the system that we just talked about looks like. Here we've got the sample represented by a red dye. Here you can see 2 different other solutions, the yellow dye and the blue dye. And you can see that our flow is laminar. There's nothing in this channel, so this is just a channel that's got a certain width. The flows are being pumped in at certain rates, and the rates then determine the width. The ratio between the rates determine the width that these flows will be present in the channel. So we've got the central dye is not going to be able to enter this separation channel because there's a shield in place. And we don't need to create any obstacles. We can just use the fluid dynamics to control what's happening. If we stop the buffer 1 and buffer 2, then the red comes here at the interface and we can inject a small amount of sample. Here you can even see that that's just happened. There's a small amount of the sample that was introduced before. And these curtains stop any transport because we are the laminar flow regime. Liquids just follow a nice straight line, and you can predict it based on the flow rate ratios. This is used in a functional element that's called the H filter. In the H filter, we've got a sample coming in with some large molecules and some small molecules. So that's called our donor phase. And we've got a channel that's called our acceptor phase that just contains some buffer. There's nothing sitting here in the middle. There's no membrane, no filter. It is just, this is an empty channel. But because we're in the laminar flow regime, at the point that our buffer and our sample come in, they're both going in a straight line, they don't look around, they don't go wandering and shopping. Laminar flow regime, they just go straight on. So we've got parallel flows here of our sample and our buffer. But if our sample contains both our acetate that we looked at earlier, that diffuses really quickly, and it contains our antibody that diffuses really slowly, we actually will get a fair amount of diffusion of our acetate into our acceptor channel, whereas our protein stays confined to our donor channel. So this way we can remove the small molecules or dilute it down to kind of equal concentrations. So we can conduct dialysis. We can remove small molecules from large molecules without the need for a membrane, just relying on the difference in diffusion constant between a small molecule and a large molecule. So there's a whole wide range of different approaches where you can use an H filter, you can extract if you want to work, so think about applications in agriculture. If you want to work with an environmental sample where there's colloids and particulate matter, the diffusion constant of that will be even lower than that of the target analytes if they're small molecules. So you can use this for sample preparation where your colloids stay in your donor phase, but your analytes are extracted into your acceptor phase. So without the need of filtration, which for colloids is not easy to do because they're so small, you can still extract your small molecule analytes without the need for any physical barriers, only relying on fluidics. This picture here I thought was quite appropriate to put in there considering we're in a visual arts environment. The Forge lab, Albert Forge works in, I think it's Massachusetts, he's somewhere in the US. And he's realized there's actually really beautiful phenomena that you can do with microfluidics. So in this instance, he has a device with a number of different valves where you can control the fluidics. But you can very nicely see that the flow lines stay separated. So if you've got different dye molecules, the flows stay separated. There's no need to have physical barriers in place. Up to the point here you can start seeing a little bit of diffusion taking place. But here you can see the flows come in and they just follow their track, just like their trains, just like their guide rails in place. And all it requires is some complex plumbing. So this is another nice photograph where you can see little blunt injection needles, some flexible tubing to connect with the fluidic features, as well as here with some of the fluidic control lines. You can see the different colors are coming in. And then here, if you would zoom in, you can see all the colors segmented nicely in a zebra-like pattern, because the only thing they do is follow the flow lines. Flow rate and pressure. We already touched on this on the first day. We can predict what our flow rates are doing. We can, based on their resistance, following the same equations that we're used to use for electric circuits. So we can have flow resistance in series, which means we can add them up. We can have flow resistances in parallel, which means we can still add them up, but we then need to do 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. Works exactly the same way for flows as it does for electrical resistances. We can calculate the flow resistance for different channels. In a cylindrical channels, the flow resistance increases with R to the power 4, whereas for a rectangular channel, it increases with the width of the channel times the height to the power 3. So we can calculate what the hydrodynamic resistance is, and that way we can calculate the resistance ratios, and the flow will divide according to our resistance ratios. So if one channel has got, as we've seen the example on Monday, 1,000,000 times the flow resistance of the other, there won't be any significant amount of liquid entering that channel because the resistance is just too high. Like with an electrical system, all the current will take the easy way and take the low resistant pathway. The flow does the same thing. The flow will always follow the easiest way, so the channel with the lowest resistance. One of the nice examples that the Mans group used early in the 90s to explain that flows and currents work exactly the same way is that they got the map of London made as a microfluidic device. So all the roads in London became channels. And they then connected 2 different points to try to find the fastest way, because that was the easiest way to go from A to B. And indeed, they could, using the different solutions, they could find the fastest way in London to get from A to B, just using the fluidics of the traffic in the city. So, in microfluidics, our flow is very different to what we're used to. We are in laminar flow, flow goes in lines. Our flow resistances determine the direction that our flow is going and the ratios in which if we enter different flows into our device, we can use the flow resistance and the pressure that we apply to control the direction where our flow is going and the width. The second thing that I would like to bring your attention to is that the surface effects are a lot more pronounced when we work at the microscale than when we're working at the large scale. And we already knew that from biology. If we look here at an elephant, and it's a little bit hard to see, but we'll get copies of the slides later on and then you can see that. This is an elephant. An elephant has got a very low surface to volume ratio. Elephant is really big and doesn't have a lot of skin to count for that. Whereas a mouse and a rat actually have got a much higher surface to volume ratio. So here we've got the body weight and here the metabolic rate. A mouse needs to work really, really hard to keep alive, to temperature control itself. Whereas for an elephant, it's not that important because the heat loss in an elephant relative to its body mass is a lot lower than for a mouse. So a mouse therefore needs to eat a lot more in order to compensate for the heat loss that it's got. In our normal beakers that we're working with in the lab that we're doing our synthetic reactions in, we're working in elephants. So it takes a while to get your solution warmed up. But once you are around 50 degrees, it actually takes a little bit to have that temperature change again. Because we don't have a lot of surface that we can lose our energy from compared to the volume of water that we've got in a beaker. If we look in microfluidics, we've got a lot of surface area and only a very small volume. So if we've got a picoliter droplet heated up to 50 degrees Celsius in a laboratory that's 25, before we even start our experiment, the droplet is already back at 25. The heat loss through the wall, through the thermal conductivity, because we've got such a big surface area, the heat loss in that droplet is so fast that we really need to have a good temperature control system in place because our surface to volume ratio is so high. So the good thing is we can do really, really fast PCR in microfluidics because we can heat something up with a laser or a heater, a resistive heater under the channel. It doesn't take a lot of effort to heat a picoliter of liquid. We don't need a lot of calories, we don't need a lot of energy input. It also cools down really quick, so we can withdraw the energy really quick as well. So we can do sub-seconds. I think we have seen cycling times of 10 milliseconds in PCR because we can control the temperature so well because of the high surface to volume ratio when we're working on microfluidics. Much, much easier than when we're working in an Eppendorf tube, a lot easier than when we're working in a 1 or 2 liter beaker. So the surface to volume ratio, if we want to look what our ratio is, if we work in a normal beaker, kind of 10 by 10 by 10 centimeter scale, if we translate it to a cube, our surface to volume ratio is 60 per meter. So if we've got 60 times the volume per meter surface area. When we work at the micrometer scale, it is 600,000. So we've got 60,000 more. Our surface to volume ratio is to 10,000 times more when we're working on the micrometer scale than it is when we work on the centimeter scale. That is where our gains in efficiency come in. Next concept is capillarity, which we all know when you put a straw in water. We have, and it's a little bit pale here with the light on the slide, but here we've got a tray of water and we've got a glass capillary. Glass is hydrophilic. So the liquid will creep up by capillary pressure up this tube to a certain height. If we change the surface to volume ratio, we go to a narrower bore tube. The amount of pressure we can generate by this wetting on the wall significantly increases, which means that our filling increases, our capillary filling height increases when we shrink down the diameter. To start thinking about all those observations, how to put that into rules and parameters. There is the capillary number, and the capillary number is the ratio of the viscous forces and the interfacial forces. Interfacial forces with a larger surface to volume ratio become more important. Capillary number is the dynamic viscosity multiplied with the velocity. So everything in microfluidics tends to depend on how high you put your pump. So what is your flow rate? And the surface or the interfacial tension. So if we increase the capillary number, that means that we decrease the surface or the interfacial tension, which means that we increase the droplet diameter because it's sitting more away from the surface. That is important to know when you're making droplets as small chemical reagent containers. If we've got a carrier flow and a sample flow coming in a droplet system, our carrier is an oil, so it is mineral oil, whereas our sample is aqueous, it's water. Water and oil don't mix, so they will form separate phases. There's the bug. At a certain flow rate regime, we get very nicely plugs or droplets being formed of our dispensed liquid. If our flows get too high, however, our capillary number changes, and we end up in the laminar flow regime where our water and our oil phase are flowing alongside each other. So it is important to understand what the capillary number of a system is, to understand if you want to do reactions in droplets. You don't want to be ending here, you want to be sitting here. So you can calculate what your capillary number is to know that you're working at flow rates that are in the plug regime, which means that you get stable droplets being formed. So the capillary number is the ratio of the viscous and the inertial forces. We've got a large surface to volume ratio, which means that our surface effects are really important. The surface tension can result from the deformation of the free liquid surface. So that's what we've seen in capillary. And by capillary action, we can actually drive fluidic motion. Not only up in your straw, but we can also use the capillary forces to have passive microfluidic devices where the flow is controlled by having either different surface geometries or coatings in place that manipulate the surface tension of the liquid that's flowing there. So capillary forces can draw liquid into wetting channels when the interfacial energy between the wall, the solid, and the liquid is lower than the solid gas interface. So we need to displace the gas that's present in the empty channel with the liquid, and that depends on the capillary forces if that works or not. So surface tension, we've got a couple of different regimes. When we've got hydrophobic material and we've got an aqueous droplet, it beats up. It doesn't like touching the surface because hydrophilic and hydrophobic surfaces don't like water. If we've got a hydrophilic coating, our water nicely spreads on the surface. So if we treat a glass slide with a little bit of sodium hydroxide, it gets deprotonated, it becomes really hydrophilic, and you get your water just to spread all over the surface. Very different to when there's a greasy coating on. So if we've got a complete wetting, we've got a contact angle of 0. And we've just got a smooth, even film of liquid sitting on the surface. If we have a low surface tension, we get a droplet being formed where the contact angle is smaller than 90 degrees. And then the more, if this is an aqueous droplet, the more hydrophobic the surface gets, the more this droplet starts beating up. So contact angle smaller than 90 degrees, at 90 degrees, and if we go to hydrophobic, we end up with the droplet having very little contact with the surface and all held together by the cohesive forces. No need to memorize all the different constants, but I thought it was good to have a look at what the differences in surface energies are of different liquids, water and some organic solvents as well as blood, and what the contact angle is of water on for example, fused silica. It's 52 degrees, so just over the 90 degrees. On untreated glass, gold is very hydrophobic, so contact angle is 0. And water on platinum or PMMA or glass, so our contact angle of water or the liquids change with the material properties. So hydrophilic is defined as a surface that water can wet, which means that the contact angle is below 90 degrees. A hydrophobic surface is a contact angle that doesn't wet, which is a contact angle over 90 degrees. Super hydrophobic is when you're over 150 degrees. So then there's very little contact left. A volume of an incompressible liquid minimizes the free energy, which means that the shape becomes a sphere if there is no reason to wet the surface. But with gravity, there we will be able to pull, it will deform, but this length is in the order, for water air, it's in the order of millimeters. In microfluidics, we're way under that millimeter size, so gravity is not really a concern. Our liquids are not really affected by gravity in the spatial domain where we're looking at in microfluidics. One of the things that we can do with an electrode is change the wetting. So we can add charge to the surface and therefore make it more wettable. And that way you can move a droplet uphill. In this case, we've got a hydrophilic region and hydrophobic region with an oil droplet. If using a potential difference, we can change this barrier. The oil droplet will actually try to creep towards the hydrophobic region, defying gravity. So there are some nice movies that I did manage to get one downloaded, but where you can actually use digital microfluidics on a flexible substrate, and you can just have droplets by manipulating the voltages moving up the hill, defying gravity based on the fact that they're small, and changing the properties, the material properties, using a potential difference. Here that's explained. So here we've got a conductive droplet. If the potential is off, the droplet will be with a contact angle of about 90 degrees. So that's the initial droplet shape when there's no potential being applied. If we apply a potential droplet, then all of a sudden the contact angle changes and our droplet will be spreading a little bit more over the electrode, which has got a whole range of applications in dispensing, moving liquids. There's digital droplet microfluidics. We already discussed very briefly about a capillary rise, where we get the smaller our capillary is, the higher, the further the liquid will progress. Again, this is governed by some equations. So when the dimensions of the tube radius are smaller than the length, the curvature can be calculated by the radius divided by the radius of the channel and the contact angle of the liquid. And you can use that to calculate if the liquid will indeed rise in your channel based on the wetting, or if it's poorly wetting, the air will actually push the liquid down into the microchannel. How far liquids can enter depends all on the material properties and the liquids that you're working with. But you can calculate how far the liquids will come, how far the capillary rise will be, based on the contact angles between your liquid and your material, and the dimensions of your channel. So if we've got a 100 micrometer channel, we can expect the capillary lines. We can expect if we put a droplet into a microchannel and nothing is happening, that it will fill the channel for about a 4 millimeter length. If we scale that capillary down to about 10 microns, so a much narrower channel, the capillary rise is longer, and in this instance, we will be able to fill 4 centimeters, 40 millimeters of our channel with our liquid. So we can pump, fill our liquid without needing to do anything at all, just by capillary rise. A very long channel, we can fill it with water. Glass is even more hydrophilic than PMMA. And for the same glass channel, if we do the calculations, we can fill 132 millimeters of capillary network, displacing air by liquid, just using the surface tension and the interaction between the water and the contact angle of water with glass. So again, these equations mean that you no longer need to be surprised if you put a little bit of liquid at the channel entrance, that all of a sudden your liquid starts moving into your channel. It will, your channels, typically you don't need to put a lot of effort in filling your microchannels. If your channel wall is slightly hydrophilic, your aqueous solution will just wick everything in seconds all the way through. So in summary, for scaling in microfluidics, our flow is determined by our Reynolds number. Our Reynolds number, if it's low, under 2000, it means that the viscous forces dominate and we are in the laminar flow regime. And that means that mixing becomes a challenge. Hence, our next session, after I hopefully we'll have some tea, will be about how we can actually affect mixing. Because we've now looked at separating molecules because of laminar flow. Of course, we've got a difficulty arising with that, is that if we can separate things based on laminar flow, how are we ever going to mix two different reagents together? Because if we've got two reagents coming in together and they flow, we may be able to do some nice synthesis on the boundary, but our two reagents are not automatically going to be mixing. So we need to come up with a whole new toolbox to facilitate mixing in microfluidic devices, because we are in the laminar flow regime. The other important part is the surface to volume is much higher in microfluidic systems than in our normal labware that we work with as a chemist. This means that we get much more efficient heat dissipation. So we need to have a good look on our temperature control. If we do some synthesis and we've got an exothermic reaction, locally it can actually get really hot and it won't be mitigated by the rest of the thermal mass of the container we're in, because we've got very little thermal mass. Surface effects are also very important, and they're important for the wetting. Wetting helps us, so if we have water and a hydrophilic channel, we don't need to put a lot of energy, we don't need to overcome any energy barriers, and our channels will just fill automatically. If we've got a hydrophobic channel, however, it will become harder and we may need a vacuum to drive our fluid into the capillary. So understanding your liquid, your fluid that you're working with, if that's a water or an oil, and understanding the material that your chip is made from. And on Monday, we'll be looking at a couple of different microfabrication methods, where we also go look at material choices. If you want to have, don't use any pumps, and you want to work with aqueous solution, you probably want to select a substrate that is hydrophilic, because that means that your surface forces will just take charge of your filling of your channel, and you can work with your devices that way. So surface effects are very important in microfluidics. It means that we're more prone to fouling, so we may need to have surface coatings in place. But there's a whole separate field that we're not touching on, which is capillarics, where you can use different coatings and channel geometries to just have complete assays taking place autonomously. That is the lecture on the fluid dynamics. I think it's good to take a little break before we go to the next lecture on mixing. And after the mixing, we'll go for lunch, and then we'll do a little bit on particle separations before we start celebrating Holi. So Thank you very much. I'm not sure if we've got morning tea or not, but I'd suggest we take a 10-minute break anyway to relax our brains a little bit. Thank you very much for listening, and if there's any questions, please do so.
Microscale, the things are totally different from the bulk.
Yeah, and that's, again, it's painful when we have to go through, look at all the physics, but it also gives us a very interesting toolbox because a lot of the behaviors provide a lot better control.
With the help of equations and examples, it was quite easy to understand.
Yeah.
The difference at the microscale and at the in the bulk.
Yeah, and I think by then if you get the textbook with it, if you're wondering about something, you can mainly use it as a reference book to just look up what the physics is.
Yeah.
So it is, and yeah, we need to understand microfluidics, we need to rewire our brain because nothing is what used to be normal.
It's physical chemistry at another level.
Yeah. But we are at another level, so we are moving, and I think that laminar flow is just changing everything, and without understanding that that's the driver and that's what's happening, it makes it really hard to design devices because you
selection of material, selection of your fluid, now mixing is a challenge that will be handled next.
Yeah, and that's why it's hard to find the best starting point with a lecture series like this, because you need to have enough interest generated that people want to start looking at the physics. But then as soon as you start talking about different microfluidic strategies that have been developed in applications, you need to have that understanding of the underpinning physics to be able to understand what problems have been overcome. Because there are a lot of problems, like mixing was probably not something that came up as being a challenge in your mind before, and it is.
How beautifully the two liquids remain separate without any physical partitioning.
Yeah.
That's the beauty.
It is really, really nice, and that's why